Okay, so we're gonna show the practical BFT protocol today, just both the basic or baseline execution of it, and then we're gonna look what it looks like when the protocol runs into the faults that it addresses. The PBFT was invented in the 1990s. The white paper was published in 1999, and in terms of historical context, it is the PBFT is here. It's building off of this problem, the Byzantine generals problem. Then we're also going to see that it segues into this larger problem of civil attack, and then to the Paxos. We're going to cover the Paxos in our next video. And then when it comes to the PBFT, as we'll see, it's another solution, or it's just the practical version of the solution that addresses the challenge of consensus as a Byzantine fault could happen. Here we have a node with a fault, and it could send worst case scenario type signals out to the other nodes in the network. And the key part of PBFT is that it required an order of magnitude less messages. It needs, where n is the number of nodes, the first Byzantine fault tolerant protocol required n cubed, which was impractical, unfeasible, which computers just couldn't do that. Once you reduce it down to n squared, it became something that could be successfully implemented at large scales. So now we're gonna go back to our radar example. We're gonna walk through this from the beginning. Changing the slides up. Okay, so there are only 5 phases of practical BFT, and it doesn't matter how many nodes you have. You could have 1,000 nodes here. You still only need 5 phases, and it's just these 3 phases we need to concern with, because the request phase, this is essentially the radar data just arriving to each node, and then the 5th phase here is just each node's reached the point where they have reached this point of distributed agreement, and now internally they do the process of updating their database. So all we need is these 3. And if you look at the PBFT white paper, you're going to see this diagram. So what we're going to go over is we're going to use the exact same diagram. We're just going to apply it to our radar example. And then also this protocol will identify in advance. When the protocol is initially set up, it identifies in advance a leader, and then they're going to have this order of backups in case the leader or maybe the backup one faults. And we're going to see this at the end of how the protocol acts if the leader or one of the backups has a fault. But for now, we're going to assume no faults with the leader. And in the pre-prepare phase, the leader is going to send the value out that it has to all the other nodes. Then in the prepare phase, all the other nodes, they're going to send their value out to everyone else on the team, all the other nodes that are involved in this as well. So now we have the commit phase, and at first, to reiterate that, is when the protocol is set up, the number of nodes are known, and then also the limits of the protocol are known as well. So like in the original BFT solution, no more than 1/3 of the nodes could be faulty. So in this case, we only have 4 total nodes, so we can only have 1 faulty node before this protocol is just going to fall apart. And if that were to happen, we talked about there being a software backup or the idea of gracefully failing, but we can only have 1 faulty node. So when we're talking commit, really we need to go back and look at what's happening in the prepare phase, because it rolls into the commit phase. So here in the prepare phase, let's just look at Hawaii. Hawaii, the first thing it does is it's going to send its own value out to the other nodes. After it's done sending, and it's also received the value from Anchorage, and then it's going to send out its value, and now it's waiting. So in the prepare phase, it is waiting to get a predetermined number of values that are coming in to see if it matches the value that it has. And in this case, and again, our value of f is 1. We can only have 1 fault, so each node is waiting to hear 2 times 1 or 2 other values that match what it originally received. So just a cleaner look at Hawaii. it received Alaska's, sent, and then now it received North Dakota's. And at this point, it has what it needs to send a commit message. It has two values that match its original value. So it's going to send this value, this corroborated value, out to all the other nodes. And at this point, for Hawaii, Hawaii knows there are more than 2 F nodes in this team that have the same value. So they all have this value. So then by a majority rule, they can assume that this value, this agreement, is correct. And then each node at this point also knows there is shared awareness and in that the end state here has been achieved. So at this point, Hawaii is going to update its state to reflect the shared radar data from the Alaska radar. And then every node also is doing the same. And then they're all going to reach this point. They're all going to update their state. And this is the basic, the baseline BFT protocol. And as quick points, each message also contains a small amount of admin data to help this protocol stay organized and deal with minor issues. So each node is storing a database, and you can see here this is a flight track of an aircraft. It's its path, an aircraft's path across the radar screen, but it's not. This is not denoted by physical time. This is denoted by what iteration the process completed, then updated, then they repeated the iteration, and then updated, then they just keep repeating the iteration. So this pathway across the radar screen is denoted by this iterations of data exchanges and reaching a shared end state. Not necessarily by physical time. And this makes it easy to catch up. So say that Hawaii, for whatever reason, missed one of the messages in the second iteration, or the message came in late or whatever, got resent. It's easy for Hawaii to get this message and then now repopulate it. So the fault tolerant protocols build in that. It's easy to have that built-in ability. And again, the protocol knows the leader. This is something that's predetermined. In our example, it's Anchorage. But if there's like a timing problem, or there's just a number of indicators that all the backups are always monitoring, and if they suspect the leader has a fault, this leader role was just switched. In this case, Hawaii would kick off in the pre-prepare phase. Anchorage would be treated as a backup, and the process will basically continue unimpeded. And what this does is just keeps the shared awareness, keeps the shared historic data accurate. Basically the process won't miss a beat. And now how this process handles a Byzantine fault. We'll use Hawaii as an example. And Hawaii is going to receive or share or broadcast or this wrong data. All these values could even be different, or the value could be completely lost. Really you have to look at this node as the worst case scenario is going to happen to this node. And then now to the 3 other nodes, they will each of these other nodes, they're still going to receive at least 2 other message values that match the value that they got as an input. And this is so they're still going to have their trigger to go into the commit phase. And they'll commit, they send and receive their commit message, and this is going to bring shared awareness to all 3. They have more than 2F matches. So they all have this value. There's a majority rule, so it's correct, and that the team, even though we're -1, our team has still reached agreement, and now it's time to go to our next iteration. So they're going to update their data set, and then once they update their data set, and again now they're going to start working on the next iteration. So an example here, we just finished iteration 1. Now we're going to start working on iteration 2, and then at some point in the future, Hawaii will recover from its crash, and it can recognize how many iterations it's missed, what iteration the team's currently on, and it's a simple drill at that point. It can get the data from the team and repopulate what it missed. So the practical BFT is a feasible solution. It requires n squared number of messages, n being the number of nodes, or just slightly more than n squared. You can look at commit here. This is where the n squared comes from. And if you recall from the first BFT solution, we had this n squared phase, but there was a phase for every node that was present, hence the n cubed. And for the protocol, all the nodes are known in the protocol. And in this example, the protocol, when it's set up, is gonna be tailored. And here it's going to set their faulty value, their F value to 1. And then this series of message exchanges will prove to each node that they all share the same value as the other nodes, and that by majority rule, this value is correct. And then the shared awareness amongst all of them lets them know they have reached agreement, they can update their data set, and now they can move on to the next iteration in the process.